Hello. In this practical, we'll be extending our knowledge of regression, moving on to multiple regression, which includes many predictors at one time, compared to simple regression that we did in our last worksheet, where we predicted our outcome from only one independent variable. And this is a great analytic tool because it allows us to fit more complex models to better predict whatever outcome we're interested in. And for this worksheet, we're actually using the same exact data set that we did in the last one. So, whereas with the last practical, the research questions asks if we can predict judge ratings from these three variables separately. In this practical, the research question is asking if we can predict ratings from these three variables together. So that's a really key word to know that we'll be considering multiple regression for these data. And in fact, when you're working with your own data set, it's much better to do one multiple regression compared to many separate simple regressions. Doing so inflates your type 1 error rate, so the chance of a false positive when you run many different simple regressions. But also, you can't account for potential multicollinearity in your data set. So today we're going to skip over all of the descriptives since you should have a general sense of your data by this point and move right into fitting the regression model. But before we move into fitting the regression model, I do want to reorient ourselves to the results of the simple regressions last week. So if you recall from last week, we ran three separate regressions predicting um, judges' ratings or score based on hours spent researching, hours spent building, and innovation. And we determined these three regression equations to predict our dependent variable. And remember from last week, the R squared for hours spent researching was 0.2734. And that's essentially saying that 27% of the variability in judge ratings can be accounted for by hours spent researching. And this was a significant model. Y-intercept here was negative 16 and a slope of 5.75. I want to bring all of these statistics to your attention so that we can compare what we saw with the simple regression to the full multiple regression model. When you fit a simple regression model, both the R squared and the beta coefficient, or the slope of the regression equation, only include that one variable. But when you add multiple variables into the same model, you're accounting for some of that shared variability, or the way those two variables move together to influence an outcome. So if you also recall from last week, research and build were significantly correlated with each other. So it will probably be the case that all of our beta coefficients will look a little bit different when we fit the multiple regression. In fact, they might be a little bit weaker. And the R squared, again, takes that multicollinearity into account as well. When we add these three variables to one model, the R squared won't just be the addition of all three of these R squareds. So let's visualize what we might expect when we fit the multiple regression model. The regression equation is going to be just a little bit longer because we're including all of the predictors, and we will only have one y-intercept, of course. And the y-intercept, or a, that's the value, the predicted value of our outcome variable, or the dependent variable, when all of our predictors are at 0. Now, when we talk about multicollinearity or shared variance, we're really referring to this overlap. So if you consider each score being all of the data within each of our individual variables, so our circle for score or ratings is all of the judges' ratings, all of the variability in ratings, all of the variability in research, the variability in build, and the variability in innovation. Each of these independent variables will overlap with our DV, but they all also overlap with each other. And that overlap is really important to understand because it means that in this area, we can't actually conclude if our predictors are providing any unique information compared to the other predictors in our model. So while it would be great to have a model with 30 predictors that perfectly predicts our outcome variable, you'll probably have a lot of overlapping variance or shared variance. And really, how much more are you adding with that addition of multiple predictors? A model with many different predictors will always explain more of the variability, but is that explained variability actually meaningful in the end? Can we actually reliably predict the outcome from the predictors that we include in the model? That's really the goal of multiple regression. And again, because of that shared variability, the beta coefficients in our multiple regression will be different from the beta coefficients in the simple regression. So let's go ahead and fit the model with three predictors. And of course, the first thing we have to do is import our data set. Okay, we now have the 5 variables. And to perform a multiple regression in Stata, the command is exactly the same. It's simply regress. You always want to put your dependent variable first. That's how Stata knows it's the dependent variable. And now all three of our independent variables in succession. It does not matter what order you put it in, that won't change the model at all. Now you'll notice the one difference from last week is the subcommand comma beta. This will print a statistic called the standardized beta in place of the 95% confidence interval. And this is really useful because we can actually compare the strength, the relative strength of all of our independent variables on the outcome. Right? So you can see the output itself looks very similar to the simple regression last week. The only difference is this addition of multiple lines in our predictor statistics. We have an F statistic of 8.62, and this is significant. Now, recall from last week, this simply means that our model with three predictors is better at predicting judge ratings than no model at all. And based on the R squared, we're predicting about 56.4% of the variability in judge ratings from all three of our independent variables together. And this is quite a bit more compared to the three simple regressions. I think Innovative had an R squared of about 0.44. So we're accounting for almost 12% more variability with this three predictor model, right? And our constant coefficient here, that's our y-intercept. So when somebody spent 0 hours building, 0 hours researching, and has an innovation score of 0, we would predict a judge rating of -14. Now, it's okay that the y-intercept doesn't make any theoretical sense. Again, this is just the predicted judge rating if somebody didn't submit anything based on our model fit. And in the same column, we also have our predictor betas. So for research, the beta is 3.45, rounding to 2 decimal places. Build is 0.17, and innovative is 6.70. And remember, the beta is simply the change in the outcome variable for a 1 unit change in the predictor. So when we look at the beta for research, when we hold both build and innovative constant, or rather when build and innovative are at 0, with a 1 unit increase in hours spent researching, so let's say you go from 2 hours spent researching to 3 hours, we would predict an increase in judge score of 3.45. Okay, and you can interpret the other coefficients just the same. And we can also determine the significance of each predictor. If each predictor is a significant predictor of judges' ratings based on our t statistic and p-value. Okay, so the t for research is 1.87 and a non-significant p-value of 0.077. Remember, in the simple regression, this was significant, but now when you include both build and innovative, it's a non-significant predictor. And I would guess that it has something to do with multicollinearity here. Remember that hours spent researching and hours spent building are highly correlated. So there's some of this shared variability that's probably mucking up the model itself. Now, unsurprisingly, our T for build is a non-significant predictor. This is unsurprising because it was non-significant last week. And then finally, how innovative the project is a significant predictor. Now let's talk about what it means for these individual predictors to actually be significant. What does that significance level actually tell us? Let's consider the null hypothesis for a regression model. With a multiple regression, the null hypothesis simply states that all of our betas will equal 0, because a beta of 0 simply means that our predictor has no influence or no effect on the outcome. So beta 1 equals beta 2 equals beta 3 equals 0. And then conversely, our alternate hypothesis simply states that all of our betas are significantly different from 0. They could be either positive or negative, but they are significantly different from 0. So beta 1 doesn't equal beta 2, which doesn't equal beta 3, which doesn't equal 0. So with our null hypothesis in mind, this non-significant, let me change the color. This non-significant p-value for hours spent researching, this means that the beta coefficient 3.45 is not significantly different from 0. Then on the other hand, the significant p-value for innovative, that simply means that our beta coefficient of 6.70 is significantly different from 0. So even though only one of our predictors is significant, the overall model itself is a significant model. Again, this just means this model with 3 predictors is better at predicting judge ratings compared to a model with 0 predictors. And with multiple regression, if you have at least one significant predictor or one significant independent variable, then your model itself will be significant. Now let's consider the standardized beta coefficient. The standardized beta allows us to compare each of our independent variables and the strength that each IV has on our outcome. And we can do this because the standardized beta works in standard deviations rather than the raw scores. Because the range of each of our independent variables might be quite different, we can't actually compare them together. So it's not very meaningful to compare a beta of 3.45 for hours spent researching compared to a beta of 6.70 for innovative, when hours spent researching is a much greater scale compared to the innovative score. While innovative is from 0 to 4, hours spent researching is something like 10 to 40. So a 1 unit increase in hours spent researching or a 1 hour increase is much different compared to a 1 unit increase of an innovation score. So going from 2 to 3, an innovation score from 2 to 3 is much different from hours spent researching 2 hours to 3 hours. And the standardized beta essentially works in standard deviations. This means that it's placing everything on the same scale, so we can actually compare. And the practical way to interpret your standardized beta is that a 1 unit or a 1 standard deviation increase in your predictor will result in a 0.31 standard deviation increase in your outcome. So for hours spent building, a 1 standard deviation in hours spent building will result in an increase of 0.11 standard deviations for judge ratings. Okay, and you can interpret each standardized beta the same way. And of course, the larger the standardized beta, the more influence it has on the outcome. So perhaps unsurprisingly, our only significant predictor of innovative has the largest standardized beta. So it has the most influence on judge ratings overall. Now, if I ran the same command without the subcommand comma beta at the end, I would get the same results, but I would also get the 95% confidence interval. And that information is still important. So it might be good for you to run both commands and interpret all of those statistics together. But for today, let's go ahead and move on to multicollinearity.